Okay, so I am going to explain the Lewis relation, which is a dimensionless number which relates thermal diffusivity and mass diffusivity. So it relates thermal transfer, heat transfer, and mass transfer, and brings the two together. So to do that, I'm going to need the equations for convective and conductive heat transfer. So for the equation convective heat transfer, it's equal to the heat transfer coefficient times the concentration, times the temperature at the surface of the object and minus the temperature of the surrounding environment. And for conductive heat transfer, write down conductive, it's equal to the negative conductivity of the object times the change in the temperature over the change in distance. All right, and so if we take a closer look at convective and conductive heat transfer, we can see that they look somewhat similar. They're in a similar fashion to two other equations that we know. So we have the molar flux is equal to the transfer coefficient times the concentration at the surface minus the concentration of the surrounding environment. And if we look at conductive, it's the diffusive flux is equal to the negative diffusivity times the change in concentration over the change in distance. All right, so if we look back at a previous example that we've done, we know that the Sherwood number is equal to the mass transfer coefficient times the diameter divided by the diffusivity. And we showed that we can make an equation using the Reynolds number and the Schmidt number and coefficients, and raising both of the Reynolds and the Schmidt number to a power. We can derive a relationship between those. And so we have a constant A times the Reynolds number raised to some power B times the Schmidt number raised to some power C. And we can also do the same thing with the Nusselt number. So the Nusselt number is equal to the heat transfer coefficient times the diameter divided by the conductivity. And we can do a similar thing that we did with the Sherwood number, but instead of using the Schmidt number, we're going to use the Prandtl number. So some coefficient A times the Reynolds number raised to the B times the Prandtl number raised to some power C. And you'll notice that I used A, B, and C in both equations. And this is because A, B, and C are equal to each other in these cases. And so let's take a closer look at the Sherwood numbers and the Sherwood number and the Nusselt number. Or not Sherwood, the Schmidt number and the Prandtl number. So we know that the Schmidt number is equal to the viscosity divided by the density times the diffusivity. And the Prandtl number, let's write Reynolds number, the Prandtl number is pretty much the same, the viscosity divided by the density, and we're going to instead multiply the density this time by the thermal conductivity. Not the thermal conductivity, it's the thermal diffusivity, sorry. Thermal diffusivity. And you can see that the terms in these are exactly the same except that the Schmidt number uses the diffusivity, that'd be the mass diffusivity, and the Prandtl number uses the thermal diffusivity. And we can reduce these two numbers down, the viscosity divided by the density. We know that to be the kinematic viscosity. It's equal to the viscosity divided by the density. So we can reduce these equations down a little bit. So it's the kinematic viscosity divided, the Schmidt number is the kinematic viscosity divided by the diffusivity, and the Prandtl number is equal to the kinematic viscosity divided by thermal diffusivity. Okay, so now what we're going to do is take the Nusselt number and we're going to divide it by the Sherwood number. So I'll just write them out real fast. We have the thermal, the heat transfer coefficient times the diameter divided by the conductivity, all divided by the mass transfer coefficient times the diameter divided by the mass diffusivity. And so we can see that some things cancel out, like the diameter cancels out. And we are left with this equation that, let's see, the heat transfer coefficient times the diffusivity divided by the conductivity times the mass transfer coefficient. Okay, and we also know, using these equations up here, if we were to divide the Nusselt number by the Sherwood number, that the first part of each of these equations would just cancel, and we'd just be left with the Nusselt number divided by the Sherwood number is equal to the Prandtl number divided by the Schmidt number, all raised to the power c. And now you can see why a, b, and c are equal to each other, because we can just put make the entire ratio, raise it to the power of c. All right, and we know what the Prandtl number and the Schmidt number are equal to. We showed that up here. So we can put these in. So we will have the kinematic viscosity divided by the thermal diffusivity divided by the kinematic viscosity divided by the mass diffusivity. That's all raised to the power c, is equal to the mass diffusivity divided by the thermal diffusivity raised to the power c. And so if we look at the definition for the Lewis number, the Lewis number is equal to the thermal diffusivity divided by the mass diffusivity. So we can see that this is just equal to the reciprocal, is that this here is equal to the reciprocal of the Lewis number. So we can show that it is actually just equal to 1 over the Lewis number raised to the power c. I'm just going to write that in a cleaner way. So we have the Nusselt number divided by the Sherwood number is equal to the heat transfer coefficient times the mass diffusivity divided by the conductivity times the mass transfer coefficient is equal to 1 over the Lewis number to the power c.